Hi everyone. What we're going to do today, or in this video, is to talk about step 2 of the matrix encryption project, which is actually the decryption part. So I'm going to skip over number 1 in the instructions where you convert your message, your ciphertext into numbers. I think you can do that. You did that when you did the encryption portion. And I'm going to jump to step 2 where we have to find the inverse of the encryption matrix that you were given. And so we'll talk about that. We're going to look at part A where it says use the Gauss-Jordan method to find the inverse of our matrix. And so what I've done here is I have my original encryption matrix, the key, from the last video, and I've augmented that with the identity matrix, the 3x3 identity matrix. And what we're trying to do is figure out the inverse of our key matrix here by performing operations on it that turn it into the identity. Performing those operations is equivalent to multiplying this matrix by transforming matrices to get it there. And if you think about that closely, you'll realize if we're multiplying this matrix by a set of matrices in front of it to produce the identity, then that set of matrices in front of it multiplied together has to be the inverse of this, because I'm multiplying my original matrix here by a set of matrices and getting the identity. So the fact that I'm getting the identity from a product of two matrices means that they're inverses of each other. And so as you can sort of treat this line in between the matrices as sort of like an equal sign, right? I'm going to multiply my original matrix by a set of transforming steps, which is equivalent to a matrix, to get the identity, and I'm going to be doing the same thing to this side. And if I'm multiplying this identity matrix by the set of steps that I'm using to turn this into the identity matrix, then on this side I'm going to produce the inverse that I'm looking for. I recognize that that's kind of wordy and hard to follow, but hopefully that makes some sense. So I'm going to go through a couple steps of this process and then jump down to what the final product of that looks like. So as we go from the original matrix through the first step, remember the goal here is to get zeros everywhere except the main diagonal. Okay, so I'm going to start, as I do with Gaussian elimination, with this bottom left-hand 9. I'm going to make a 0 out of that. And the way I'm going to do that is I'm going to add -9 of the second row to 1 of the third row. Okay, and this is the result of that. Over here, I'm doing the same thing. -9 of the second row is -9 times 1 in this column, right? -9 times 0 is still 0. -9 times 1 is -9. -9 times 1 is 0. But I'm also adding 1 of the third row, right? So I'm getting the 0 plus this 0, the -9 plus this 0, and the 0 plus this 1, and that's where this is coming from. Okay, so -9 of these and 1 of these into my third row. Okay, my next step is I want to get a 0 where this 1 is. And so how am I going to do that? I decided I'm going to take 1 of my first row and add it to -2 of my second row. Maybe I should write that down. This was row 3 gets, what did I just say? -9 row 2 plus 1 row 3. This step, I'm getting a 1 in this position, so I'm going to take row 2 and I'm going to transform it into 1 row 1 minus 2 of row 2. And that's what you see here, right? I'm turning 1 row 1, so 1 plus 0 is 1, 1 plus -2 times 1 is -2, 1 times 0 plus -2 times 0 is still 0 here, right? And I'm doing the same thing on this side, and that produces this 0. Next, I want to come down to this -23. I want that to be a 0, right? This one's kind of a pain in the butt because I've got large numbers here that I have to, and this is a prime number, so I'm going to have to multiply the second row by 23 and the third row by 6, right? And that's what I ended up doing, right? So I'm taking 23 of the second row and -6 of the third row and adding those together. And this gets a little complicated because these rows have already changed, right? So 23 of the second row and negative 6 of the third row, if I look at the first column here, I get 23 times 1 plus negative 6 times 0 is 23. 23 times negative 2 is 46, plus negative 6 times negative 9, 54. 54 plus negative 46 is positive 8, right? And then 23 times 0 plus negative 6 times 1 is negative 6. Okay? And so that's how I'm performing this. And as I keep going, I keep producing more and more zeros. I've already got these 3. I want to get these 3, and then I'll have the main diagonal set. And you can see this is the result of that without going through the rest of the steps. I've gotten zeros in these 3, and this is the result. Now normally if I want to find the inverse, what I would then do is just divide, I'd take row 1 and multiply it by 1/27th of row 1, and I would end up dividing 2 by 27, negative 4 by 27, and 3 by 27. I would take row 2 and I'd make that 1/45th of row 2, and I'd have negative 19 over 45, 11 over 45, and 3 over 45, etc. Problem is, if I do that, I get all these fractions. And as you guys know, the fractions don't correspond to any letters in our alphabet, and so we can't do it that way. So what we need to do instead is not multiply by the inverse of these numbers in the real number system, but multiply these numbers by their inverse in the mod 29 number system. And that's what we're going to talk about here in a second on the next video. Actually, you know what? You might want to watch the video on Euclidean division algorithm first, so you understand where that's coming from. So I would watch that video and then look at the inverse mod 29 video. Thanks.